Hello, and welcome to the final explainer video. This is going to be for question 3 on long homework 4. So question 3a asks us to solve these expressions right here. And so we know that when we evaluate this bra and ket acting on each other, we're going to end up getting the Kronecker delta. And we know from the definition of the Kronecker delta that if the indices are the same, then we get 1, and if they're not the same, we get 0. So in this case, we have side 3 and side 3, so we know that the Kronecker delta will give us 1. Now for this case, we have side 2 and side 3, and so because these indices are not the same, we will get 0. Now for this third part, we have the Hamiltonian operator inside here, but we know that from the eigenvalue equation, we can then just replace this with the eigenvalue lambda. And so in this case, we're going to end up getting lambda 3 with the Kronecker delta 3, 3, which gives us just lambda 3. Now for this fourth one right here, we're going to end up getting the Kronecker delta 2, 3, and so we know that regardless of what lambda is going to be, we don't actually care, because this will just end up going to 0 anyways. So whatever lambda is, this expression will just end up being 0. So these four are the solutions to these four expressions right here. Question 3b asks us to use the perturbation theory to write out the eigenvalue equation in full. And so usually we just write h, right, the Hamiltonian. But the full form of h is that we have h plus this factor right here, so epsilon v. And so what we can do with this is we can then expand this formula right here by plugging this in, and as well as this in for lambda. We can hit both sides with row vector psi. Using the definition of the eigenvalue and the operator, we can rewrite the expression to have lambda rather than the Hermitian operator. Since we know that the Hamiltonian is Hermitian, we can use this property right here to help simplify our expression even more. We're still assuming that epsilon is very small, so any term with an epsilon squared out in front will go away. And the remaining terms we're going to have are going to be this one and this one, we can just cancel those out. And so our final expression is going to be as follows. Question 3c asks us to determine the full eigenvectors to leading order, and we have to figure out what the state perturbations are in the unperturbed eigenbasis. And so we can use these identities to help us out. This time, instead of hitting both sides by psi upper I, we're going to be hitting it with psi upper j. Now, we can use these expressions to rewrite this to simplify even further. We know from earlier that the Kronecker delta will equal 0 if I is not equal to j, which is true in this case. So this will allow us to cancel out any of these terms right here. This problem is mainly about the perturbation theory, where small changes can be made to approximate a complex scenario using a much simpler one. This comes up a lot in physics, and some examples include a particle in a box with a bump, where there's a tiny potential bump instead of the usual flat box, anharmonic oscillation with a nonlinear restoring force, the Zeeman effect, relating to spectral lines emitted by atoms in a magnetic field, and the Stark effect, the electric field analog to the Zeeman effect.